We are glad that our revered Secretary Maharaj is here, so it pronounced to him. Then we'll start today's session of Vivekananda Science Circle. Now, and this is also a memorial lecture for not eight, for two persons. So I will first actually describe to you their background, whose names the memorial lecture would carry, and then I will introduce the author to you. So, thank you. So, first let me introduce the persons in whose name these lectures are dedicated. Dr. Souvik and Dr. Prasanta Kumar Biswas Memorial Lectures. This is the memorial lecture for India name. So just a short background or history of Dr. Souvik and Dr. Prasanta Kumar Biswas. I will read it out for you. Dr. Souvik Maal হাওড়া জেলার বেগরি গ্রামে 5ই ফেব্রুয়ারি 1985 খ্রিস্টাব্দে জন্মগ্রহণ করেন। পিতা ডাক্তার সমীর কুমার মাল ও মা শ্রীমতী কৃষ্ণা মাল ছিলেন। মেধাবী ছাত্র সৌভিক মাল রামকৃষ্ণ মিশন রহরা থেকে 2000 খ্রিস্টাব্দে মাধ্যমিক ও 2002 খ্রিস্টাব্দে নরেন্দ্রপুর রামকৃষ্ণ মিশন বিদ্যালয় থেকে উচ্চ মাধ্যমিক পাশ করেন। উচ্চশিক্ষার জন্য এন্ট্রান্স পরীক্ষায় উত্তীর্ণ হয়ে কলকাতা মেডিকেল কলেজে ভর্তি হন এবং 2007 খ্রিস্টাব্দে MBBS পাশ করেন। ডাক্তারি শাস্ত্রে উচ্চশিক্ষার জন্য তিনি রিজিওনাল ইনস্টিটিউট অফ অপথলমোলজি শল্য বিভাগে মাস্টার অফ সার্জারি ভর্তি হন। 2012 খ্রিস্টাব্দে চক্ষু বিভাগে শল্য চিকিৎসা হন, মানে অপারেশন আর কি, এবং কৃতিত্বের সঙ্গে সেই দায়িত্ব পালন করেন। তিনি মাত্র 1 মিনিট 25 সেকেন্ডে একটা ক্যাটারাক্ট অপারেশন করতে পারতেন। 2013 থেকে 2018 খ্রিস্টাব্দে পর্যন্ত তিনি সরকারি বাঁকুড়া সম্মিলনী মেডিকেল কলেজ তাতে চিকিৎসক হিসেবে মানুষের সেবা করেছেন। ডাক্তার সৌভিক মালের উদ্যোগে ও ঐকান্তিক চেষ্টায় বাঁকুড়া সম্মিলন মেডিকেল কলেজ প্রথম ছাত্রদের জন্য মাস্টার অফ সার্জারি পড়বার ব্যবস্থা হয়। দক্ষিণ 24 পরগনার ডায়মন্ড হারবার মেডিকেল কলেজে তিনি 2018 থেকে 2020 খ্রিস্টাব্দ পর্যন্ত চক্ষু বিভাগের প্রধান ও সহকারী অধ্যাপক ছিলেন। 30 জুন 2020 খ্রিস্টাব্দে অতি অল্প বয়সে, খুবই অল্প বয়স তখন, আমাদের সকলকে ছেড়ে চলে যান। ডাক্তার সৌভিক মালের অল্প পরিসর কর্মজীবনের মধ্যে সেবার মনোভাবই প্রকাশ পেয়েছে। তিনি তার নামে যে স্মারক বক্তৃতা হচ্ছে সেটা তার পিতা সমীর কুমার মাল ও মা শ্রীমতী কৃষ্ণা মালের পৃষ্ঠপোষকতায় আয়োজিত। আরেকজনের নামও আজকে আছে, তার নামে স্মারক বক্তৃতাটি আছেন। তার নাম ডাক্তার প্রশান্ত কুমার বিশ্বাস। ডাক্তার প্রশান্ত কুমার বিশ্বাসের জন্ম 7ই অক্টোবর 1933 খ্রিস্টাব্দে। বাবা ডাক্তার প্রভাত কুমার বিশ্বাস এবং মা পারুল বিশ্বাস রাঁচির বিশপ ওয়েস্টকট রাঁচি নামকুম স্কুলে পড়াশোনা শেষ করে পরবর্তীকালে ক্যালকাটা মেডিকেল কলেজ থেকে ডাক্তারি পাশ করেন। এরপর ডাক্তারি শাস্ত্রে উচ্চশিক্ষা লাভের জন্য বিদেশ যাত্রা করেন এবং লন্ডন থেকে MRCP DPH ডিগ্রি লাভ করেন। ডায়াবেটিস রোগের চিকিৎসায় তাঁর আগ্রহ ছিল বেশি। জীবনের শেষ দিন পর্যন্ত রোগীদের সেবা করে গেছেন। সাহিত্য, সঙ্গীত, ক্রীড়া ও ইতিহাসের প্রতি তার গভীর আগ্রহ ছিল। উপস্থিত বুদ্ধি সম্পন্ন মানুষ ছিলেন, তার ব্যবহারের মধ্যে তা প্রকাশ পেত। সর্বদাই ঈশ্বরের প্রতি বিশ্বাস রেখে ইতিবাচক নিয়মানুবর্তিতা এবং অনাড়ম্বর জীবনযাপন করেছেন। ডাক্তার বিশ্বাস 9 ডিসেম্বর 2015 খ্রিস্টাব্দে ইহলোক ছেড়ে অমৃতলোকে যাত্রা করেন। ডাক্তার প্রশান্ত কুমার বিশ্বাস স্মারক বক্তৃতা তাঁর কন্যা অধ্যাপিকা নীলিনা ঘোষের পৃষ্ঠপোষকতায় আয়োজিত। আজ ডাক্তার সৌভিক মাল এবং ডাক্তার প্রশান্ত কুমার বিশ্বাস স্মারক বক্তৃতা দেবেন আর একজন ইয়াং প্রফেসর অভিজিৎ মুখার্জি। তিনি ডিপার্টমেন্ট অফ জিওলজি অ্যান্ড জিওফিজিক্স, স্কুল অফ এনভায়রনমেন্টাল সায়েন্স অ্যান্ড ইঞ্জিনিয়ারিং, IIT খড়গপুরের সঙ্গে ওখানে তার কর্মস্থান। তো সাবজেক্ট হবে গ্রাউন্ড ওয়াটার সিকিউরিটি ফর ফিউচার ইন্ডিয়া। Groundwater security for future India. Now I'll introduce the author, quickly because I don't want to take much time. But I'll just you know from the poster advertisement that his name is Professor Abhijit Mukherjee. He got his PhD from University of Kentucky. And he's a professor in the Department of Geology and Geophysics, which I already mentioned to you, so I won't repeat. Now, he has a lot of good credentials, and he's pretty well known now. He's very briefly, actually, I will be telling you what it is. He is a fellow and counselor of Geological Society of America, and then also fellow of the American Geophysical Union and fellow of the Royal Society of Chemistry, UK. Now, in addition to that, he has some other, qualifications that I should say, that he is an associate editor or editorial board member of several very well-known journals. One is Scientific Reports of Nature. Nature is a very well-known journal. Now, Scientific Reports of Nature, and then ES, Environmental Science and Technology Engineering, and Journal of Earth Sciences, Springer. Springer is a very well-known book publisher. And otherwise is Groundwater for Sustaining Development. He's also there. He's in the editorial board, and that the last one is published by Elsevier. So these are pretty well-known book publishing companies, and he has something to do with all of them. And so with that brief introductions, and I'll request Professor Mukherjee to give his lecture, and thank you.
Thank you so much, Dr. Larry. It's my distinct pleasure to be here on this, in this audience and in this auditorium today. As Dr. Larry already introduced, I'll be talking about something that I have been working for almost last 2 decades on groundwater security for India. But before I do that, I would definitely like to pay my homage to one of the most elaborate scientific mind of India. I'm specifically saying the word scientific here because I think many of the science that we are doing actually emanated from this great philosopher. So with that small tribute, I would like to go to my primary talk with your permission. So the work that I'm going to present today is definitely not just my work. In today's time, science has to be always done by collaboration. And this work is actually a continuation of the work that we have been working for the almost last 2 decades, like I said. And rather than acknowledging my collaborators and acquaintances over each slide, I would like to summarize them in this title slide. So I have worked, or my group has worked with all these agencies along with many other organizations, and what I'm going to present is a culmination of that work. So the topic of today's work is water. Now, we come from various disciplines, we work in various disciplines, but at the end of the day, all of us are working for a habitable earth, and that is going to be the future of this planet, the future of humanhood. And again, like we differ in our opinion, we differ in our practices, our background, but at the end of the day, we are all looking for, these 6 pillars, at least these 6 pillars, which definitely starts with water, air, energy, food, climate, and health. We need to secure this, not just as India, but across the world. And we are all working in various ways to achieve these goals. Of this, in today's talk, I'll specifically like to highlight the issues of drinking water and the issues of accessible food. But then I'll also touch upon, briefly, at least on breathable air, and climate, because this is the buzzword for the time being. And what I'll try to show is that how each of these are interconnected to each other. So, like the title slide said, that this talk would be mostly concentrated toward water. And water is a free commodity as of the day, at least in India. And people are using water in various ways, wasting it to a large extent. But what is the future of water? The future of water is definitely groundwater. Why? The reason being that 99% of the fresh water in this planet, usable fresh water in this planet, is actually groundwater. That leaves only 1%, which is in other forms like rivers, lakes, and other sources. So groundwater is overwhelmingly our source of water for the present times as well as for the future. As the statistics runs, almost 70% of the drinking water in this planet as of today is actually supplied from groundwater or its subsidiaries. So it is a topic that might be of interest to various people of various background. What I'd like to talk about is how we are exploring that water in India and how we're using it for the society. Now, when I say talk about groundwater and saying that 99% of the liquid fresh water is groundwater, I would not claim that this is a knowledge that is just restricted to the modern days. Rather, the concept of groundwater was also present in the times of our ancestors. The first figure that I'm showing you is a motif taken from the Jor Bangla temple in Bishnupur. And the terracotta motif depicts the Battle of Kurukshetra, where Grand Uncle Vishnu is lying on the arrow bed, and Arjun is piercing the ground to bring out water. That is groundwater. So even in the context of Mahabharata, the concept of groundwater was there. And in Kurukshetra, even today, if you go there, there is Vishakund, where you will see the groundwater is emerging from the subsurface. But then, if you look at the history of India, when I say India, it's the greater South Asia, there is ample example of usage of groundwater in our history. That starts from the days of Indus Valley Civilization in Mohenjo-daro, known as the City of Wells, where more than 800 groundwater wells has been excavated out. And then it continues throughout our known history of India, telling us that the concept of groundwater in some form or other and its usage as a drinking water source was there even in our historical past. But then we are looking for the future, right? So let's move forward to the future. Let's come to the 20th century. And when I say groundwater, when I say water, the most obvious feel is that that's drinking water. While yes, groundwater is the primary source of drinking water, but it is also overwhelmingly used for food production, for industrialization, for urbanization, and name any. So in today's time, if you look at India's economy, 9% of the GDP is actually connected to groundwater directly, and indirectly more than 50%. So in some way or other, our economy, our society is being driven by water, groundwater. So where is it used? Well, if I look at this chart, it's a little old, but I think it's still relevant. The water consumption says that 85% of this groundwater actually is used for food production, not for drinking. So when we are talking about water, groundwater, it is actually food that we are talking about. I like to tell my students that we are eating water, as we in Bengali we say, jol khachi. So yeah, we are eating water through food, and of course also drinking it. So conserving our source of water, source of drinking water, actually is essential for our survival. Now, that's a very broad term. So let's look at the general issues of groundwater in India and across South Asia. So the first thing which is very obvious is water scarcity. And as we just moved from the summer, we are presently in monsoon, but even up to like a month, 2 months away, water scarcity has been a big deal, and it has been across the country, across South Asia, that people have been reeling through drought, not having sufficient water. But then, in some parts of the country, few hundred kilometers this way and that way, you have water excess. And when there is a water excess, as it is happening today in Telangana and Andhra Pradesh, the primary thought is that it is mostly from some kind of climatic event, some heavy rainfall or something. Well, that is true that most of the floods are from climatic sources, but it's also a matter of fact that the trigger of such flood actually is connected to groundwater. There is a physical process that results to the flooding of the surface. Either way, whether it's a scarcity or excess, that's a more theoretical thing. But on the ground, what is important is the drinking water security. And the drinking water security is telling you that if you have excess water or less water, either way, people don't have their sources of water. And I don't think I need to explain that securing our drinking water source, the simple reason that I have this water bottle in my hand, tells you that if nothing else, we have to secure our sources of drinking water. But then, just having source of drinking water is sufficient? Possibly not. So I'm showing you some photographs that I shot myself from people of this state who just drank bad water. Okay, that's their only fault. So people drinking bad water can eventually die through a very painful death. And this is the outcome of drinking carcinogenic arsenic within drinking water, groundwater. So, like all these issues do have many facets. It's just not the science, but also the society at large. And then, in modern times, we also talk about the climate change. And this climate change, not that I understand very well climate change, and I haven't found a lot of people who really understand climate change, but that's something happening, and climate is changing, whatever that means, and people are talking about a lot of things. Now, I don't understand that all of those things, but what I do understand that if climate change is happening, would be happening, one of the first victim of climate change would be the water cycle, and so would be the groundwater. So all of these things that I just showed you actually going to be accentuated in a distant or maybe near to distant future. So the water problem, the groundwater problem are not going to get resolved until we intervene, but going to get amplified in the days to come. And this is more true as we speak about the United Nations Sustainable Development Goals. as many of you might know, for those who don't, there are 17 goals that has been actually defined by the United Nations, and all the 183 countries who have signed the proclamation are bound to follow these 17 goals. These are 17 grand goals that we in planet Earth, as our country, irrespective of the nation, irrespective of the caste, creed, religion, nationality, we all are bound to follow or try to address these goals. So these are the grand goals for this planet as a humanhood. And goal number 6 is access to clean water and sanitation, specifically. Whereas all the other 16 goals are somewhere or other connected to water. So when we talk about the access to clean water and sanitation, even in the present times, with all the effort that we are talking about, out of the 8 billion people in this planet, more than 5 billion people still don't have proper access to clean water, of which 2.4 billion people don't have access to water. Okay? So it is not something very theoretical, something from the book, but it's something on the ground. So we are blessed to have our source of water living in the city. But if you look at the villages of this country or our neighboring countries to many other parts of the world, there is a very grim picture. And we, as a student of science, we are supposed to resolve this problem. So the matter of fact is that by 2030, that is the deadline, which is 6 years away, we are supposed to resolve that all 8 billion people, that is the population of the day, should have access to clean water and sanitation. Obviously, we are far behind. But again, in this country, many of the national missions are actually trying to target and implement that. It comes in various forms. Possibly people don't get it connected directly, like, for example, the Jal Shakti mission, the Jal Jeevan mission, Swachh Bharat Abhiyan. They are all actually names, various names for accessing this goal number 6. So when we talk about groundwater, we are also trying to establish and find out solution for resolving these UN SDG goals, specifically goal number 6. But then India is reeling through its worst nightmare. As many media sources have highlighted in the last about 15 years, that India is going through a period which is called the worst groundwater crisis in modern times. So there is a drought below the surface. So a drought on the surface, over the surface, you get to know. But something below the ground, you don't know. Outcome? Cities like Bangalore drying out. Cities like Delhi, you have fight, like neighbors versus neighbor, just to secure their source of water. So my group and I have been working for almost the last 2 decades, a little more than that, on how much safe groundwater is available in South Asia and what is the future. It's a simple question, but possibly not an easy one to solve. And I would definitely like to highlight the word safe here, because safety is paramount important. So we have to find out both quantity and quality. Now that brings a question that, is it an emergency? And why is it an emergency? Because you would think, living in a city, that okay, most of our sources are kind of secured, we don't have to worry about it. But the matter of fact is, if you take a more larger contextual view, you will see that the Indian subcontinent, which is India plus its 6 neighboring countries, sister nations, we have 3% of the global terrestrial landmass. However, it is only about 23% population of this planet who are living in this 3% of the land. And we are using, we are actually contributing to 30% of the global irrigated land by groundwater. So in no sense, 3% of the terrestrial land can host 1/4 of the global population and 1/3 of the food production. It doesn't make sense. Definitely, something is lost. So if you look at these 2 maps, the maps that are posted on the right, you would see that the first map is the population map. And again, it's no wonder that India is today having the largest population of this planet, along with China, competing with China in some sense. But on the same note, the map on the below here, it also shows the areas of this planet where you have the most crop production. And you can see that along with China and North America, parts of North America, India is also a leader. So what is going on? At what cost? This figure highlights you the groundwater consumption of this planet, the largest groundwater consumer of this planet. And what you do see is that there are 6 countries that are listed, 7 countries. And India actually has groundwater usage in present times and projected future that is more than if you add up the second and the third user, which is US and China together. Or in other words, India is the global leader. So we are consuming as much water that both China and US together is not doing. And is it everywhere? Well, not. So if you look at this map, and the first map shows you the most intensely groundwater irrigated area of the world. And what you see is that the color ranges from light color here, which is very less, to very deep color here, which is very high irrigation. And there is only one part of this planet where it's very consistently maroon, right? This part. Every other part of the world, there is only specks. So it is the northern India, or northern Indian plains. Just not India, but starting from Pakistan to Bangladesh. And these northern Indian plains actually is the most irrigated part of this planet, consuming out most of the groundwater. Consequently, at present day, India is the largest consumer of groundwater, not only in present times, but in the human history. So we are consuming out this resource, this natural resource, at a rate, at a volume that is unprecedented in this planet. Nobody has seen this before, and hopefully not in the future. And that needs people like us and other experts of similar skill set to come forward and take a look how to solve these problems. So the first step to solving this problem is trying to understand it, that what is going on. What I'm showing you are 2 maps. The first map is a geologic map, and this geologic map shows you what you call rock types, or like geologic media, where it will host groundwater, called aquifers. And what I like to highlight you, there are various colors. What I like to highlight you are the 2 blue colors, the bright blue and the deep blue. The bright blue constitutes the river valleys, the 3 mega rivers that is flowing in South Asia, the Indus, the Ganga, and the Brahmaputra. The 3 rivers coming down from the Himalayas creates one of the largest, what we call sedimentary systems of this planet, and also are the largest host of groundwater, one of the largest hosts of groundwater in this planet. Whereas this deep blue color area, which is mostly in central and southern India or South Asia, these are what we call the ancient rocks, the cratonic rocks. And these are, the very old rocks, like billions of years old. So these 2 geologic formations actually kind of covers most of the subcontinent. And what you would like to know is the distribution of land and the groundwater. So the bright blue area, the Indus Ganges Brahmaputra basin, hosts about 27% of the Indian landmass, but hosts or contains about 70% of the groundwater. Whereas the deep blue area is almost like 67% of the Indian landmass, but hosts only 20% of the groundwater. So you can see the disparity. It's a very bipolar distribution where The northern Indian plains, even though it is geographically very limited, it hosts a huge volume of groundwater, whereas the southern parts of the country doesn't have a lot of groundwater. The distribution of this water is also very obvious when you look at the population density, because this is the northern Indian plains where you have some of the densest part of this planet in terms of human settlements. Now, the dichotomy is that if you look at the map on the right, you'd see that same areas where you have natural pollution. And these pollutions can come in the form of arsenic, in the form of fluoride, salinity. The interesting part is that these bright blue areas, the Indus, Ganges, Brahmaputra basin, and its surrounding, are the areas which are also poisoned by these natural sources, pollutions, like arsenic, like fluoride. Consequently, what you have, that there is a lot of groundwater in these bright blue areas, but the groundwater is very limited for human usage. The next step to understand this is the science of it. Now, I'm not going into nitty-gritty details of the science, the physical and the chemical aspects of the flow and so on, but what I would like to highlight that there are three processes that are important. The first one is the recharge. The recharge happens because of rainfall. The cycle starts with the rainfall. And the rainfall, the groundwater would flow through the subsurface in thousands to millions of years. It doesn't happen immediately. It takes a lot of time, actually. And as it goes through certain chemical reactions, very complex chemical reactions. Again, I'm not going to details of that. And eventually, that is discharged in the rivers or oceans. And these completes the groundwater cycle that we don't get to see. Is invisible. So this whole concept that I showed you, along with the physics and the chemistry, is something more mathematical, more scientifically observed, but not visible to human eye. But there are manifestations, and these manifestations, I'll just explain you in a minute. But before that, if that is a natural process, there are some more processes that have been influencing the groundwater resource in a large way. And that's, of course, starts with climate change. 1970s onward, we're talking about climate change, and we believe that climate change is making a lot of repercussions. But then, human practices and policy interventions. Till last year, not last year, 2022, the largest geoscientific bodies of the planet, that includes the US Geological Survey, they considered the groundwater system or the hydrologic cycle to be something which is very much planet Earth, no human. In 2022, they revised that philosophy, and they published a more modern version of the hydrological cycle that is influenced by human practices and policies. So, in present times, as a student of geoscience, we cannot think planet Earth without human. It is an integral part of the system. Many people argue otherwise, but somebody who is practicing this for the last almost 25 years or more, I cannot see how we can explain Earth without human. So human influences are visible in every aspect. What I'm showing you is a 20 years list of groundwater recharge patterns that we calculated out across India. Now, there are presumptions, there are limitations to these techniques, but by and large, it does shows you that how groundwater recharge has been happening in this country between 1996 and 2015, where you do see that the northern Indian plains do have a higher rate of recharge, by and large, whereas the southern cratonic rocks, the older rocks, do have a lesser rates of recharge. What is also visible that the recharge patterns, the colors, are not same for every year. So there are interannual variabilities. And there are very distinct reasons for those variabilities. But then, if this water sinks in the subsurface, sips in the subsurface, it goes through multiple levels of reactions. And these reactions would change the chemistry of the water, the chemistry of the groundwater. So much so that many of these reactions would actually leach out the poisons from the rocks or poisons from the sediments. So we hear a lot about fluoride contamination, arsenic contamination, specifically in West Bengal, in the Bengal area, West Bengal and Bangladesh. Let me tell you that most of these pollution are actually natural. They happen because of natural processes, very complex chemical processes. And that is actually visible by very detailed science. But when I say that these processes are natural and it has to happen because of natural interactions of water with the sediment, it is also true that we humans are making it worse. And over again, we have realized that if natural processes have started leaching out the poison to the subsurface, to the groundwater, it's the human practices in terms of irrigation pumping and other things that we do, we have actually made it worse and made this poison spread out in a larger context. So what I'm showing you is the first map of arsenic across India. It is a work that we have done with the Jal Jeevan Mission. We integrated there about 2.7 million data samples that they have collected over last so many years. And what I do show you the patterns, and this has been done through a combination of physical geology plus numerical data science, integration of the two. And what I show you the patterns of the distribution of arsenic across India. There are very distinct patterns. This pattern ranges in the North Indian plains. As you can see that it continues from, of course in Pakistan, but in the Indian side in Punjab, continuing through the Ganga Jamuna sub-basins to eastern UP, and then following up to West Bengal and to the northeastern states, specifically Assam in the Brahmaputra basin. There are some also arsenic which are found in the Maharashtra, Gujarat, Madhya Pradesh belt, and definitely something in the south, in the Bangalore, not Bangalore, in the Hatti, Kolar goldfield areas. So again, you see, like, they are not random. There are patterns. And we as a scientist are there to try to identify and understand this pattern. Why is it important? Because if we can realize the patterns and we can find out the background that would cause such patterns, we are possibly going to develop some kind of remediation techniques, some kind of engineer or natural solutions that would provide the safe drinking water to the people. But then, if this is natural, there is also pollution from human sources. Now, something that we don't realize in India that well, but in the Western countries, in the more developed countries, the emerging pollutants are actually causing havoc, more havoc than the natural pollution. Why? Because the natural pollution can be engineered quite easily. Because they are coming out from nature, we can put it back to the nature. But the compounds, the organic compounds that we are creating from a human engineering source, that are very difficult to remediate. And it's a matter of fact that the Ganga Basin, we did a pilot study in the whole of Ganga Basin in West Bengal, it's actually severely polluted by emerging contaminants like pesticides, like antibiotics, like PAHs, polyaromatic hydrocarbons. And those pollutions are present both in the river water and groundwater, something that we are quite unaware about. And something else which we don't talk about. Now, we all know about the Swachh Bharat mission, and we feel that the Swachh Bharat mission is specifically for constructing toilets. But there is also a background story to this. Yes, Swachh Bharat mission is about accessing clean sanitation. But clean sanitation for what? Is it for aesthetical value? Possibly yes, but also for protecting your groundwater from sanitation-based pollution. It's a matter of fact that in the last few hundred years, there has been pandemics across South Asia from waterborne diseases. You talk about the cholera, you have to talk about the acute diarrhea that have actually killed generations. Now, in present times, such, if not in pandemic mode, but at least there are sections of this country, of course also in neighboring countries, where we do see the prevalence of sanitation-based pollutions. However, the good thing is that as time is passing and we are realizing all these problems, we are actually constructing through Swachh Bharat Mission and other modes sanitation structures or methods by which we have been able to restrict the introduction of sanitation-based pollution to the groundwater sources. So it's a positive thing, but again, we cannot be reluctant that, okay, it's doing very well, so we should stop. It's something that we have to continue for the next few generations. So with that introduction, I would specifically now move on to a more specific study and talk about some of the work that we have been doing, which also makes a difference. So rather than going for one specific study, I would like to talk about a combination of studies that we have been doing on groundwater quantification. Okay, we talked about the pollution, not much on the quantity side. And over the last 20 years, more specifically last 15 years, we have been working across India through all kind of geoscientific methods, starting from very classy, very out-of-the-book geological methods like subsurface exploration, deep exploration, to very modern techniques like earth observation, remote sensing, geophysics, different types of groundwater monitoring, and then integrating all of those to the buzzword, data science, and integrating all this data by modeling and big data analytics. So what we are trying to do is data analytics, AI for sure, but not blindly, but influencing that with the physics and the chemistry. So we are tying back to the more theoretical geoscience to the very modern data science. The example that I'm going to show you is a collaboration that NASA and we have been working for the last 14 years. And this is a project that I have been involved since 2006, when I used to work at the University of Texas at Austin. And since my then supervisor was one of the project investigators, so in 2002, NASA sent out 2 satellites. And those satellites were initially destined for 5 years. However, those satellites and the follow-up from those satellites are still moving around the planet. These 2 satellites are named as Tom and Jerry. And this Tom and Jerry does a very funny thing. Now, it's very detailed science, but I would like to explain that in a more general terms. So what it does, it measures the gravity of the planet. And the gravity, in some sense, is actually providing you a measure of the groundwater storage. I'll show you the equation in a minute, in a very general term. Now, these 2 satellites are moving over us at an elevation of 500 kilometers. And they are tied by a laser beam 220 kilometers apart. And these 2 satellites move around 15 revolutions per day. And as they go forward along their orbit, they measure the Earth's gravity many times a day. What you're looking at, this sphere that is kind of rotating, is not not the Earth globe, but it's what we call a geodesic globe, gravity globe. So it's basically the gravity value of this planet mapped in 3 dimensions. So how does it work? It works in a very simple equation. Of course, to solve this equation, you need supercomputers. So yeah, they look simple, but they are not. So what it does a combination of these measurements that they do from the satellites in terms of gravity, but then equate it back with simulated values, supercomputer simulated values of soil moisture, surface runoff, and snow cover, do a bit of math, and calculates out what we call the change in groundwater storage. So these colors that we're looking at, the red is telling you that some place as the groundwater is depleting, the blue as the groundwater is increasing. And as you will see, these changes in colors from this animation from NASA, that over any point on the Earth's surface, this color changes over a period of time, within a year. So these changes are every month over a period of time, which tells you that groundwater is not a very constant factor. It changes continuously Nothing is constant. But this is satellite-based value. How much do you trust on it? So we have been the Indian collaborator of NASA. ISRO is now also a part of this work, and we are also working with ISRO on this. So what we try to do is to track back this study with the ground observations. So with our links with the Central Groundwater Board, Government of India, Minister of Water Resource, now called Minister of Jal Shakti, we try to ground truth the satellite data with the Indian groundwater observations, field observations. And we looked at about 20,000 locations across the country and found out that in most areas, the correlation is about 0.7 to 0.8, which is a very good correlation, taking account of all these uncertainties. Telling you that the satellite is doing a reasonably good job. So let's look at how the groundwater scenario looks like over India. This is the decadal scale groundwater storage change that we computed between 2003 and 2014. Again, newer data are now available, so we are now expanding our observation to 2022. So next time if I come and talk here, I'll show you till 2022. But as of the time, it's still 2014. What I would like you to look at are these changes of color. Don't go in the details of what they mean. It means that the blue is good, which means that there is more groundwater, and the red is kind of where you are drying out for groundwater. You'll see that the colors are changing, and color changed from one place to the other. In the same place, they changed much more. But there is some consistent pattern. The consistent pattern as it shows that the northern Indian plains are drying out. Even in this data of about 12 years, it showed that the Indus, Ganges, Brahmaputra basin actually has dried out. And if I had shown you the data till 2022, which is the latest data we have, you'd see that this redness has increased. But then the good thing is that some parts of the country, specifically the southern and central part of the country, this redness actually has turned blue, which means in these areas, specifically these areas, you have the groundwater getting rejuvenated, which is in contrary to many of the things that we hear. So let me walk you, in the next few minutes, let me walk you through some of this. This is, again, a little complicated, so I'll just try to break it down. So the plot down here, it is showing you the groundwater trends across the Indian region. And what you do see that there is a depleting trend, but it's not very strong. However, if you look at the trends of northern and eastern India, you would see a much stronger trend. Eastern India more specific. Now we hear that in Punjab, Haryana region there is a lot of groundwater that is being taken out, they are drying out very fast. But a matter of fact, it's the eastern India which is drying out faster. And of course, northern India is also losing a lot of groundwater, but the trends, the rates are more steep in eastern India. However, central, west, and southern India actually is gaining some groundwater, and situations are getting better. So, there are a lot of colors, a lot of patterns. So we break it down. We break it down to just blue and red. Red being the areas where we call them having groundwater storage decrease, and the blue area where we have calling groundwater storage increase. And we ought to understand both the conditions. The areas which are red, we can call them the groundwater drought. These are consistent red that has started from at least 2003 and continuing. And it's getting actually worse. Now what is the cause? Now the cause actually is not just linked today, but something that started in 1970s. It started with our government introducing what we call the Green Revolution. This Green Revolution started with introduction of water-intense high-yielding crops. Now it has a very strong positive side of it. How? Well, before 1970s, 1965 to be more precise, India was a food deficient country. We have to import most of our food. But at the introduction of the Green Revolution, initially by Lal Bahadur Shastri, our Prime Minister Lal Bahadur Shastri, and then by Mrs. Indira Gandhi, India became a food deficient to a food sufficient to food exporter country. So, yeah, that's a lot of development. Somebody who has to bake for food now is exporting food to other countries, but with a cost. The cost was groundwater. And we produce the food at the cost of a huge volume of groundwater to be abstracted from the subsurface. Now, most of this groundwater was used and being used for what we call flood irrigation. And you would see, acres after acres, miles after miles of paddy fields with a lot of water, even in the dry seasons. Where is all this water coming from? They are coming from the groundwater. Something that is being recharged for thousands of years and now being taken out for your food production, which is never going to go back again. Or it will, but not in a human time scale. It will take another 1,000 years to go back. In some specific locations within this red zone, they also actually use this groundwater and go for water-intense cash crops. Now, people is all about money, and we need to earn money. Some people need to earn more money. And these people, in addition to producing their food, they also want to create, more money. And what they would do, they would convert their food crop to cash crop, something like sugarcane. Okay? So in areas which are initially not naturally meant for paddy field, they are growing rice. One good example is Punjab. And not only rice, basmati rice, which is a water hog. So in areas which were not actually naturally designed for other than anything like wheat or barley, there's a lot of basmati rice being produced from those areas. Western UP, which are okay for rice, now they are growing a lot of sugarcane. All of this, of course, to generate fund, but at the expense of groundwater. So, as we are drafting the policies for this nation, it is also important to understand the society and the need of the society, because you cannot, just serve the science or the technology. Society comes hand in hand, and it's important to understand what the society is looking for. And some people do talk about the climate change, and they consider that, much of these groundwater issues are actually being produced, being caused by climate change. Now, I don't believe that. Now, climate would have some impact, but again, to see the impact of climate change, it takes about 30 years. What I showed you is only 12 years of data. So if climate change was the trigger, then we would need a larger time series of data to demonstrate that. It's not there yet. I'm not saying climate change is not doing anything, but we are still yet to see the impact of that in the subsurface. Now, what I'm going to show you is something possibly less intuitive. Now, this is kind of intuitive. People talk about this. There are several news articles, debates that happens in the TV all the time. But what I'm going to show you, another impact of this groundwater storage change, something that you would not think about. Well, the matter of fact is, a river like Ganga, like Brahmaputra, like Indus, they are believed to be glacial-fed river. The matter of fact is that they survive on groundwater. There is a very detailed science, physics that can be explained out of it. I'm not going into so much details. The matter of fact is that because of this groundwater pumping, the rivers are drying out. And we are already seeing that in the Ganga basin. I have been told by my colleagues in ISRO that they are observing very similar thing in Indus and Brahmaputra. So we have recently signed a MOU to look at that. So the major rivers of this country are actually drying out. Now, this is also a phenomenon that is happening in few other parts of the world. But for India, this is extremely scary, because the photographs that I was seeing it, they are shot in the month of May, few years back. And you can literally see these are the beds of Ganga from Bihar to West Bengal. And people are literally walking on Ganga. Okay? You might always argue that, okay, that's a very temporary thing. It happens only for a couple of days. But it should not have been happening. And if you look at a time series data, that couple of days is increasing a day to day, another day every year. It is adding up. So in present times, Ganga is drying out. Like I said, there is a very detailed physics that goes within. I'm not going into that. What I'm going to talk about is the outcome. The outcome is that if Ganga is drying, it is not only just, a river is drying out, but it is going to also kill our food source. So by 2050, that's our prediction, 115 million people in the Ganga basin are going to starve from severe to acute food insecurity. So when we are talking about securing our water source, we are not just talking about the water source that we see, but it's also the water source down below, and of course, our food security. Another interesting aspect that you would like to know is the air pollution. Again, you would think, okay, why would air be anyway connected to water? Well, the matter of fact is that New Delhi, which we all hear about a month from now, you cannot go to Delhi. If you go there, you have to wear a mask all the time, because otherwise you will be choking. You come out of the flight, you'll be literally choking. It has happened to me. You come out of the airport, you'll feel like suffocated, because you cannot breathe, because the whole city is like a gas house. Now, you think, yeah, definitely it's air pollution. And you think, oh, it's all the vehicles moving around, all the things that Delhi people are doing, the political parties are doing. However, I have gone to Delhi in my childhood, and I cannot recall that. Now, of course, that was like 10, 15 years back. And you would think, like, okay, so what has changed? What has changed in between is something that changed in 2009 in a change in the water policy. Actually, food production policy. So in 2009, 2010, the states of Punjab and Haryana brought in something called groundwater protection laws. And what they did is they literally changed the cropping cycle. And this cropping cycle, which was otherwise previously based on groundwater, they tried to peg it back to the rainwater, so that you can decrease the groundwater usage, thereby rejuvenating the groundwater sources. What happened, because of this modification of the cropping cycle, the two cropping cycle, the summer monsoon to winter, which otherwise was spread out like with a window of about a month to clear up the stubbles, now got squeezed to a week. Consequently, the farmers, who some of them might be doing it willfully, some of them are forced to do, they don't have other way to clear out the stubble other than burning. Outcome? 2010 onwards, whole of Punjab and Haryana are burning the stubbles, the rice residues. Consequently, from about that area, New Delhi to the whole Ganga basin up to Calcutta, there is a brown fume that is passing through. And this is also the time when you have the change in the wind direction. The southwest monsoon wind is replaced by the northern winds. And these northern winds moving from Afghanistan to Pakistan, to the Punjab, to Delhi, to Lucknow, to Patna, to West Bengal, is bringing down these fumes from Punjab to the Bay of Bengal. So the air pollution that you see in the northern Indian plains, specifically in Delhi, actually got caused by modifying the groundwater cycle. So again, the laws were made for a good reason, but with unwanted consequences. And now they don't know what to do. They're talking about a lot of things about managing those stubbles, but it is a lesson learned that if you don't think about the collateral damages, it can come and haunt you in a much bigger way. But then I don't want to make this talk totally something very gloomy, and like to end with a more positive message. And I would like to highlight you the scenarios of groundwater replenishment. What I'm showing you, that blue areas that I have shown you earlier in the slides, and these areas which believed to be having groundwater storage increase. Now, when I showed this information firstly to the government of India, they were not very sure. Really, this is happening? And then I showed them our study with the the Minister of Water Resource, and our mathematical calculation on how the ground data is matching with this satellite data, and showing you where all these blue and red dots are showing where groundwater has increased over the years. Of course, it is kind of spread out, but there are some patterns that also emerges from this. So let me show you two examples, one from Gujarat and the other one from Telangana, Andhra Pradesh. And as you would see that these two areas, both the satellite and the groundwater are showing positive results, and they are showing that groundwater is actually rejuvenating. Now, why is it happening? When we went to go and investigate that in the field, we found out various reasons. Some of them are related to the government or more changes in policies, but most of the other ones are more local, more neighborhood kind of thing. NGOs are doing things on the ground that ranges from rejuvenating riverbeds to rainwater harvesting. Specifically, one scheme that I should mention here, again a collateral thing, the Manrega program. The Manrega, the Mahatma Gandhi National Rural Employment Scheme that you otherwise would know as 100 days work. This 100 days work was instituted by back in the early 2000s as an employment generation project, one of the largest social scheme in the world in giving employment. What they did in turn is they used this 100 days work in most of the places to dig up ponds. Now, digging up pond is a good thing because it also generates employment. You dig up the pond, you use a place for water harvesting, you have fishes and so on. They never had it in the mind that these ponds would actually act as a groundwater source recharge. But when we started doing that, we understood that this Manrega program introduced ponds as a collateral benefit has actually recharged the groundwater in a lot of way. This actually triggered the Jal Shakti project, the Jal Shakti mission in some way. So again, something that you initially don't plan for, but can pan out as a good or a bad thing. I would also show you another example, which again is something possibly was not really intended for groundwater benefit, but it happened that way. That is the Jyotigram project that was instituted in Gujarat back in 2002-2003. This Jyotigram project, the two pillars that you are seeing here, like in many of the states, electricity is free for agricultural purposes, and that electricity feed is for 24 hours a day. And some of this farmers' protest that is happening now actually is because of that. Because in 2002, the then government of Gujarat understood that providing this 24 hours agricultural electricity is making things worse, because people are pumping out groundwater whenever they want. Instead, what they did, they split out the electricity feed for domestic use electric feed, which is 24 hours a day, and agricultural electricity feed, which is only restricted for 8 hours a day. So even if you have 24 hours a day power at your home, you can only use your pump in the field for 8 hours a day. And what we have observed that over the years, that actually potentially resolved and rejuvenated the groundwater of Gujarat. So if I summarize this whole thing and show you some numbers, so as of the present times, about 13 cubic kilometers of groundwater are being withdrawn from northern and eastern India. Now you can imagine the volume, 13 cubic kilometers. I don't know if you can even imagine the volume of groundwater. The good thing is about 3 cubic kilometers of groundwater is coming back. So at the present day, every year we are losing 10 cubic kilometers of groundwater. So this work did get a lot of international attention, and what you're looking at is from the NASA website on the 22nd of September, so just about 6 years back, when the study became the NASA website picture, and it did, got a lot of media attention that, okay, maybe there is a silver line after all this dark discussion. So what I would like to end with is that with proper management, proper will, and of course scientifically prudent policy, we can possibly still conserve this natural resource which otherwise would be lost forever. I'll stop that and would be very happy to take any questions that you might have. Thank you.
Myself is Bhaskar Sen. I am a mechanical engineer by profession, but worked for rice mills, captive power in Bangladesh and few places. Do you have an insight that there is a big lobby with wheat, but rice doesn't have a lobby?
Okay.
And these are two major crop patterns throughout the country which plays havoc.
Please raise your hand or come ahead actually if you want to ask a question.
Excuse me.
Yeah.
Achha, we got lot of rainwater during monsoon. We can hold it in pond or in some reservoir, and some sort of treatment. Is it feasible to recharge it in the aquifer by mechanical means, so that we can partially can solve some problem? Is it feasible?
Technically, yes, but in practice, it's questionable. So, in theory, yes, it is absolutely possible, but there are several ground realities that need to be resolved if you want to do that.
Bypassing the ground surface.
Yes, so like I said, like theoretically it's possible, but there are few considerations, some based on science, some based on certain societal aspects, which makes that happening to be a little limited. So, from the government of India, specifically in South India, they have a lot of investment on what we are mentioning about is rainwater harvesting or managed aquifer recharge. In Bangladesh, they tried it very hardly, very widespread. But to my knowledge, it has not been thoroughly successful because of certain problems. There are positive signs, but it's still yet to be rolled out to the ground.
So, we have a major source of water in sea.
Right.
On earth is all the 3 parts is sea, 1 part is just land. So I believe that commercially viable arrangement to convert the sea water in the usual form. This is one question. And second question is there any link between groundwater and sea water? That is the second question.
Right. So I'll answer your second question first. So when I showed you the groundwater cycle, so the last part of the cycle I did tell you that the groundwater goes out. That goes out either in the river, in the nearest form, or in a more distant form, it goes out in the ocean. And it's a matter of fact that the shallow ocean water is actually largely groundwater. It is actually the discharge of the groundwater to the ocean. And the shallow water ecology in the ocean actually is controlled by this groundwater discharge because the nutrients actually come from groundwater. So in many countries, so now coming back to your first question, in many countries they are trying to reclaim that groundwater that is flowing to the ocean. Countries like Greece, they are trying to do that. Not fully successful, but they are trying to do that. So going back to your first question, whether we can use seawater. The concept is called, in a very broad sense, called desalination, where you desalinize the seawater or deep groundwater, which is saline, and use it for human sources. Again, theoretically, it's possible. Technology exists. But as of the day, the technology is too costly. Okay? So the energy cost for every liter of water that you desalinize is higher than the cost of the water itself.
So in future, there is a hope.
There definitely is. So as I speak, I know some of my colleagues are trying nuclear-based or other solar-based or unconventional energy source-based desalination techniques, more efficient filtration techniques, which will take less energy. So it's possible. But then there is another practical consideration. if you think about these desalination techniques, possibly, even at the present level of knowledge, they are only viable for the coastal areas. Now, if you think that you have a country like India, where, okay, the first 50 kilometers around the ocean, sure, you can pipe in the seawater. What about an area which is 200 kilometers of the sea? To pipe in such a water to the mainland, you need a huge energy source. You need to run pumps, like with very high power. We are yet to go to that level of, the technology is there, but to manifestation of that technology. So, in principle, those are the future opportunities. Hope that we can reach some solution. But at present times, other than some smaller countries doing that, like Saudi Arabia is doing it, Singapore is doing it, in a country like India, that's something that we still have to wait for a few decades.
Thank you very much for this well-organized presentation. I am feeling very proud that once I taught you in the college,
yes, sir.
And it is a very happy moment for me.
Thank you, sir.
Now the question, sir, at the initial stage you were showing that the Gujarat area and also they show arsenic contamination.
Some areas, yes.
From my geology knowledge, I do not find any mineral concentration over there which may contain arsenic, like arsenopyrite or any other minerals, the sulfide group. This is the first part. Why did you mention it? And now we find that in the southern part, the groundwater potentiality is actually increasing. But the geology has not been changed in this area. The crystalline rocks are there. And there is a side event also, whether the Eastern Ghat and Western Ghat, do they play any role in recharging the groundwater and all that?
Okay.
That is the question.
Okay. So the answer to your first question, now even in the areas that I showed which are more contaminated by arsenic, it's not actually arsenopyrite or any of the very active arsenic source minerals. These minerals actually came as secondary or tertiary minerals that came from the Himalayas at some level and got conserved in the sediments, like clay and sand. And with specific electrochemical conditions of the aquifer, these elements got released to the groundwater. Now, obviously that is understandable for the Himalayan system, where you know that the Himalayan rocks are there. Some of them are known to have this arsenic-borne or fluoride-borne source rocks. You are very right to point out that Gujarat, specifically northern Gujarat, if you had looked, Saurashtra region, followed up from parts of Maharashtra, Nasik, and going to Madhya Pradesh, up to Ranjangaon, like in Chhattisgarh. That's a zone that previously people only knew about spots, but they never knew that that's a belt. So when we first saw this, like after creating this map, when we saw this pattern and we were amazed ourselves, what's going on? Nobody talked about this before. And then we realized that there was an ancient mountain zone, which is now kind of, I would not say extinct, but it's not talked about much. It's called the Central Indian Tectonic Zone. And this Central Indian Tectonic Zone, as you would know very well, actually extends through this area, pre-Narmada Fault. And our understanding is that the similar processes that what happened or what happened in the Himalayas, what happens in Alps now, not Alps, sorry, Andes, the Andean mountains in South America. So similar tectonic processes happened in the Central Indian Tectonic Zone. And the same process that bringing out the arsenic in the Andes in South America, in Bolivia, Chile, Argentina, to the Himalayas in Pakistan, India, Bangladesh, Nepal, actually also happened in the Central Indian Tectonic Zone. So what you're looking at, those arsenic belts, are actually remnants of those ancient formations. I don't know if it makes sense, but that's the general observation. So as I speak, one of our former students who has rejoined me as a PhD student very recently, she is now a senior geologist at the Geological Survey of India. She actually has started doing her PhD looking at those rocks. So hopefully in 3 years' time, I'll have a much better answer for you. But on a very initial note, it's the Central Indian Tectonic Zone that are the source rocks of these areas. The next question, if I understood, was about the South Indian areas. Now, what happened, like I said, the geology did not change, definitely. What did change is the policies. And in these areas, people are more conscious about water than what we are in Kolkata, or this area, where we have plenty of water. So if you go to Hyderabad or Bangalore, or mostly in the rural areas, you would see they have a rainwater harvesting at every household, that kind of thing. They're very concerned about their water sources. And over the years, let's for the example of Andhra Pradesh, they have built with local government help what they call recharge ponds. And these recharge ponds and the rainwater harvesting structures at almost every household actually has resulted in a policy intervention in reverting the groundwater depletion. So I believe, and there are documented knowledge on that now, that human policy, either from the absolute grassroots level to something on the government level, has actually changed the scenario in some of the states. And your third question is the Eastern Ghats and the Western Ghats. Nothing that I know of, like upfront, but definitely the Western Ghats, the rainfall patterns in the Western Ghats are definitely changing. And I know, like in places like Maharashtra and going up to Kerala, the rainfall pattern is changing, and possibly they would have some impact on the groundwater sources. As of the day, I don't have an answer for you on that, but hopefully in a few years' time we'll get a signature that we can come more prepared in answering.
Thank you.
Thank you, sir.
I think we should end here because I think it's getting late. But I really, this is a new thing for me. So I was highly educated now, but not highly, little bit educated about this thing, but which is very, very serious things. Could be very serious. So I think most of the people have left. So we should end it right now, and with a big clap for this. Thank you very much.
Thank you.